Hello, my name is Ramana Jamhati, and the topic that I've done a presentation on is Kirchhoff's loops. Abstract. Kirchhoff's loops, or Kirchhoff's voltage rule, essentially states that the sum of all of the voltage differences in a circuit subtracted from the initial voltage will equal zero. The equation that you can use to visualize this conceptually is V minus IR1 minus IR2 minus IR3 equals zero. The analogy that I came up with to explain this topic is a circular mountain hike. Introduction. The reason that I chose Kirchhoff's loops as my presentation topic was that I felt that it was an easy enough topic to do my slides on. However, as I researched them further, Kirchhoff's loops became much more fascinating and relevant to me, and their applications in the real world became much more profound to me. The reason I chose a hiking example is because I like to hike and trek, and by putting this topic into something I understand well enough, Kirchhoff's loops became much clearer to me. Physical principles. One of the main principles behind Kirchhoff loops is the relationship between current, voltage, and resistance. Voltage can simply be described as the pressure from a power source that pushes electrons across the circuit. Current is the rate of flow in the charges, and resistance is the opposition to that flow. The equation to keep in mind is going to be V equals I times R, where V is the voltage, I is the current, and R is the resistance. To simplify and to better visualize this topic, it would be helpful to visualize a river in your mind. The current, in this case, would be how fast the river is flowing. The resistance can be viewed as a dam that controls how much water is let through. And the voltage can be visualized as the difference in height from the source of the river to the end point. The greater the difference in height, the greater the potential energy of the water. To understand Kirchhoff's loops, let's do an exercise. Let's visualize a circuit with a power source of 24 volts and 3 resistors of 4, 5, and 6 ohms, respectively, connected in series. To find the current in the circuit, our equation will be I equals V divided by the sum of R1, R2, and R3. By plugging our given values into this equation, we get a current of 1.6 amperes. To prove Kirchhoff's loops, let's use the equation V equals IR1 plus IR2 plus IR3. By plugging in our given values into this equation, we get 24 equals 1.6 times 4 plus 1.6 times 5 plus 1.6 times 6. By solving this out even further, we get 24 equals 24. By moving 24 over to the left, we get 24 minus 24 equals 0. This proves Kirchhoff's loops because once we found the sum of our voltage drops across the series circuit, and once we subtracted it from the initial voltage, we got a value of 0. Example. The example that I used was a circular hiking trail. As you go along the hiking trail, you will encounter ascents and descents. In the case of the circuit, the descents are voltage drops and the ascents are voltage spikes. However, in the end, you end end up with the same voltage. This applies to Kirchhoff loops because as charges traverse the circuit, they will encounter voltage drops from appliances and resistors, and voltage spikes from additional power sources. However, in the end, the circuit will return to the original voltage. These are the revisions I made to the original slides. And thank you for listening to my slides. Have a great day and great summer. Thank you.